This is JBSC, John Black Superchemist, and we're here to talk about P2P synthesis in 90 minutes. Keep in mind, I've never seen this reaction or heard of it before like a week ago. I hate to, I'm not the type of person who just looks up experiments and does them. You know what I mean? Like, I'm trying to learn all the chemistry, so I gotta do like an order. So I don't like doing that. But this reaction was so easy or whatever, it's unbelievable. Does it work with benzene and acetone? I don't know. I believe it does, and we'll go over basics of it, then I'll go over the versatility of it, the reaction, what I believe the mechanism or close to the mechanism, and then I'll go over the exact instructions on how to do it. And I will go over, because these aren't my instructions, you know what I mean? I'm just looking it up. And then I will go over things that I don't like that they're doing in the experiment. Things I think they could do better or maybe change to see it make it be better. But anyways, here's the gist of it. Let's start the video. So hopefully this is how the reaction would go. Benzene would be your double bond. Acetone, and I drew the hydrogen on there because to show that it's acidic. Mix them together. Manganese 3-acetate or manganese triacetate, whichever you want to call it, is the oxidizer. And what's nice about this oxidizer is that, and you have acetic acid as your solvent. But the nice thing about this oxidizer is that it takes off one electron instead of taking off two, leaving a free radical. Okay. Now you can see that hydrogen is dangling off of there. What the Man 3-acetate is going to do, it's going to pluck that hydrogen right off of there, and it's going to take a electron with it. So you're going to have a proton and an electron, a full hydrogen, and that'll be a radical, right? Not a proton. It's taking the proton and an electron, one electron. So now you're losing a free radical. What happens to the free radical? One of the acetates takes the proton and becomes acetic acid, and now you only have 2 acetates instead of 3, right? And the electron goes to the manganese, right? Now instead of it being at 3, it's at 2. It's been reduced. And what happens is you form this, it's kind of like an enolate, you know, instead of it being negative, it's a free radical. So it's like a free radical enolate. And this wants an electron very, very, very bad, okay, to fill its octet, right? Where's it going to get electrons? Well, there's a lot of electron density from this benzene, a lot of pi. Electrons are floating above and below the plane of the molecule, so it can go in there and grab one of them, right? Now, I'm not sure how the mechanism goes or whatever, but it detects the benzene, and you can see there's a hydrogen, because each one of these carbons has one hydrogen attached to it, right? So when this attaches, now it has a hydrogen and this acetone attached to the same carbon. Where the free radical goes, I don't know. It might be over here, or it might be where I have it. Either way, it doesn't matter, because the same thing's going to happen. Another manganese 3-acetate is going to come along. It's going to grab a hydrogen radical, you know, proton and electron, and it's going to do the same thing. The proton goes to the one of the acetates to make acetic acid, and so now you only have 2 instead of 3, and the electron goes to the manganese and reduces it from 3 down to 2. And what are you left with? You're left with P2P. Now there may be a way to regenerate the manganese 3-acetate by adding potassium permanganate to the plot. That way you can keep remaking as you make the Mn2, you can oxidize it with the permanganate in situ. But I don't know how to do that. I'm not sure, but it sounds like a good idea. Now this reaction, I'll get into the exact instructions at the end of the video, but first I want to go over some of the, because this reaction is very, very versatile. Okay, it's like the Henry reaction. The Henry reaction, you can, you do it, and then you can do 3 different things to make 5 different things. You can dehydrate it to make a nitroalkene. You know what I mean? You can oxidize it, reduce it, a bunch of stuff to make different things. This is the same type of reaction. You can make a lot of things by doing almost the same reaction. Here's an example. And also I wanted to bring up that, and I'm just guessing on this, but when you have your ketone, your carbonyl compound, right, and the manganese 3 acetate comes in to take off a hydrogen radical, right, which leaves a radical, I would guess that it would take it from the more substituted side. You know what I mean? It's not going to take it from here. When over here, you can stabilize this radical over here more than you could over here, obviously. So I'm guessing it always goes towards the more substituted side. But here's an example of, like, you can add these 2 chemicals together. You can make this with the double bond, or you can make it without the double bond. You can have your double bond, right, and make a lactone. Now lactone, it's nice because it's a cyclic, you're making a ring, making rings and carbon-carbon bonds, that's like the ultimate, the holy grail of chemistry to me. And a lactone is basically just a cyclic ether, okay? So you can make an ether, not an ether, it's a cyclic ester, I'm sorry. So you can make an ester from a double bond, you know what I mean? And acid, you'd have to have some acetic acid to be a reaction with that. And you can see the acetic acid is right here. There's 1 carbon, 2 carbons, and here's the carbonyl group. And these bonds are going, that's where the double bond came. Double bond flipped up, flipped up. Okay, now here's a great example of how versatile this reaction is. Let's say this is your carbonyl, your ketone, and you put it in with the Man3. The Man3 makes this alpha oxo alkyl radical that we mentioned. See how it's got the radical there? It reacts with the double bond, right? Now you have this over here, it attached, right? The 2 pieces attached, and you could make it go from there to where you're just getting rid of the free radical. You're adding another hydrogen radical to make a single bond, right? Or you can add some copper 2 acetate into the solution, right? And you can make that into a double bond. You know what I mean? Or you can have more Mn3 in there, and it reacts and makes this, a carbocation. And then the carbocation has 2 choices. It can either react here to make, to add an acetate, right? To add acetic acid, right? The anion. Or you can take a proton off and you end up with a double bond in a ring. See how versatile, there's like, just with the same chemicals you can do, just by adding this or that, you can change your product into many, many different things. You know what I mean? This reaction is very, very versatile. It's not just to make P2P. There's a million other experiments that you can do. I remember how I said in the one reaction, that it makes a type of an enolate free radical, right? So this reaction works on enolizable carbonyl compounds really well. Okay. I just wanted to bring that up, but here's another example of why I think this reaction will work, okay, on benzene, okay. Here in Wikipedia it says aromatic compounds are useful free radical acceptors in Man3 mediated coupling reactions. So, and it gives this example right here. And you can see instead of a ketone, it uses an ester as the carbonyl compound. And you can see it gets 92%. This is the aromatic compound it gives an example of. Alpha position, it's 100% alpha position, you get a 92% yield. So it works really well. You won't get that kind of yield with benzene. And acetone, I don't think. I think you'll get more like a 30 to a 40% yield. But this is why I believe that it could work. Keep in mind, benzene, reacts with radicals all the time in reactions, you know what I mean? Like chlorination of benzene, you make a free radical chlorine. Chlorine grabs the proton and makes the benzene into a radical, and then that radical grabs another chlorine, and now you have chlorobenzene. So it reacts with, I can name 100 reactions where free radicals are attacking benzene. And like I said, aromatic compounds are useful in this Man3 coupling reaction. Here's an example, 92% yield. So this is why I do believe that the reaction will work. Okay, I also wanted to bring something else up that is in Wikipedia. It says Man3 acetate may be used either as its dihydrate or as anhydrous. So trying to get it anhydrous is no sense. It just sounds like extra work. If you wanted to make it anhydrous though, when you make the Man3, you would need anhydrous acetic acid, and you would throw that in with your mixture of Man2 acetate and your acetic acid, your potassium permanganate, and you would make it dry. You know what I mean? You would make it anhydrous. It's hard to get. You know what I mean? And anhydrous acetic acid. So and you don't need it apparently because you can use the dihydrate. So I don't see the sense in making it that way. So this is a good thing. You can use the dihydrate. I just wanted to bring that up. Now I keep saying anhydrous acetic acid. And what I mean by that, I don't mean glacial acetic acid where you took all the water out. I'm talking about acetic anhydride. Okay, that's when you link up two acetic acids together. That's the anhydride. That's what I mean when I say dry or anhydrous. I really misspoke there. This would be the best stuff to have. Because from this you can make anything. You can make anything below it, which would be this or whatever. Or any kind of acyl transfer, this is the best thing to have. But anyways, if you wanted to make the salt dry, instead of the dihydrate salt, you would have to toss some of this in with the glacial acetic acid that you're using as a solvent. Throw some of this, not anhydrous acetic acid, but acetic acid anhydride. And then your salt, your Man3 salt, will come out anhydrous. Okay, I just wanted to clear that up. Most people probably understood that I was talking about the anhydride, but I just wanted to make sure. Get back to you on part 2 and we will discuss the exact instructions. Means y'all have a great day, and always remember, science is great, and don't miss part 2.